Hello there, and welcome to the Sleepy Science Facts channel. Tonight we will be drifting outward into the universe itself. Not just the planets and the stars we can name, not just a galaxy we call home, but the whole of everything that exists, the entire expanse of space and time and matter and energy that stretches in every direction without a known edge and contains more than the human mind was built to hold. The universe is 13.8 billion years old and still expanding. It contains more galaxies than there are grains of sand on all of Earth's beaches. It began from a state so hot and dense that the laws of physics as we understand them cannot describe it, and it will end in ways that depend on properties we have not yet fully measured. Between that beginning and those possible endings lies everything that has ever existed, every star that has ever burned, every planet that has ever formed, every moment that has ever passed. This is a place where time itself had a beginning, where space is not a fixed stage but a dynamic fabric that stretches and curves and ripples, and where questions about what is real and what is possible have no easy answers. After centuries of observation and theory, our understanding of the universe has reached extraordinary depth. Yet the closer we look, the more we find that the familiar gives way to the strange, and the strange gives way to the stranger still. From the first fraction of a second after the beginning to the last cold silence of the far future, the universe rewards curiosity without ever becoming fully known. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your breathing to slow and allow the day to gently fade away as we explore the mysteries of the universe together. Let's begin. The universe began approximately 13.8 billion years ago in a state of extraordinary density and temperature, and the first moments of its existence remain beyond the reach of our best theories. What we call the Big Bang was not an explosion of matter into empty space. It was an expansion of space itself, with everything that exists emerging from a state in which the concept of before and outside had no meaning. In the first fractions of a second, the universe was so hot that even the fundamental particles that make up atoms could not yet form. As it expanded, it cooled, and cooling allowed structure to emerge. Within the first second, protons and neutrons condensed from the hot plasma. Within 3 minutes, those protons and neutrons had combined into the nuclei of the lightest elements, primarily hydrogen and helium, in proportions that we can still measure today. The ratio of hydrogen to helium in the universe matches the predictions of Big Bang nucleosynthesis with extraordinary precision, which is one of the strongest pieces of evidence that the early universe was indeed extremely hot and dense. But the very first moment, the point of zero time, remained beyond our ability to describe. The physics we use to describe the universe breaks down at those extremes. And what if anything preceded the Big Bang is a question that sits at the boundary between physics and philosophy, one of the deepest questions that can be asked. In the first tiny fraction of a second after the Big Bang, the universe may have undergone a period of extraordinarily rapid expansion that set the stage for everything that came after. This period is called cosmic inflation, and it proposes that the universe expanded by an enormous factor, far faster than the speed of light, in an interval of time so brief it makes any ordinary timescale seem geological by comparison. Inflation was proposed in the 1980s to explain several features of the universe that the standard Big Bang model alone could not easily account for. The universe looks the same in every direction to a very high degree of precision, which is puzzling because regions of the sky that are now so far apart that light could never have traveled between them since the Big Bang nonetheless have almost identical temperatures. Inflation explains this by proposing that all those regions were once in contact in an extremely tiny volume before inflation stretched them to their current separations. Inflation also smoothed out the geometry of space, explaining why the universe appears to be flat rather than curved in either direction. The quantum fluctuations that existed in the pre-inflation universe were stretched to cosmic scales by inflation and became the seeds of the large-scale structure we see today, the scaffolding of galaxy clusters and cosmic voids that fills the observable universe. Inflation is strongly supported but not yet confirmed with certainty, and the details of what drove it and how it ended remain active areas of research. The universe is not made mostly of the matter we can see. The atoms that make up stars, planets, and every living thing account for only about 5% of the total energy content of the universe. The rest is divided between two mysterious components that we cannot directly observe. Roughly 27% is dark matter, a substance that exerts gravitational effects on ordinary matter, but does not emit, absorb, or reflect any form of electromagnetic radiation. We infer its existence from its effects. Galaxies rotate at speeds that cannot be explained by the gravity of their visible matter alone. Galaxy clusters bend light more strongly than their visible mass would predict. The large-scale structure of the universe, the pattern of galaxy clusters and cosmic filaments, matches simulations only when dark matter is included. Despite decades of searching, no dark matter particle has ever been directly detected. The leading candidates, particles called WIMPs and actions, have been hunted with increasingly sensitive detectors without success. The remaining 68% of the universe's energy content is dark energy, an even more mysterious influence that is causing the expansion of the universe to accelerate. We know it exists because of what it does, but its nature is entirely unknown. The universe is therefore mostly made of things we cannot see, cannot touch, and cannot explain. The matter we know and study represents a small island in an ocean whose nature we have not determined. Light takes time to travel, which means that looking into the distance is the same as looking back in time, and the universe is a horizon beyond which we cannot see. When you look at the night sky, the light from the nearest stars left them years ago. The light from the Andromeda galaxy left it over 2 million years ago. The light from distant galaxies visible in deep field images left them billions of years ago, when the universe was young and those galaxies were in early stages of their formation. The most distant light we can detect, the cosmic microwave background radiation, left its source about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and space became transparent for the first time. Beyond that distance, the early universe was opaque and no light can reach us from earlier times. This creates an observational horizon, the edge of the observable universe, not an edge of the universe itself, but a limit on how far back in time our instruments can see. The observable universe has a radius of about 4 to 6 billion light-years in every direction from Earth, a sphere of space and time that contains everything we will ever be able to observe directly. The universe almost certainly extends far beyond this horizon, but we have no way of knowing by how much. The world we see from Earth is a window of finite size looking out onto something that may be infinite. The cosmic microwave background is the oldest light in the universe, and it fills all of space equally in every direction with a faint glow that carries a detailed record of the infant universe. When the universe was about 380,000 years old, it had cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Before this moment, the universe was a hot plasma through which light could not travel freely, constantly being scattered. The moment neutral atoms formed, the universe became transparent, and the light that had been trapped in the plasma was released to travel freely in all directions. That light has been traveling ever since, cooling as the universe expanded, shifting from the visible and infrared into the microwave portion of the spectrum. Today it fills the universe at a temperature of just under 3 Kelvin, about minus 270 degrees Celsius, arriving equally from every direction in the sky. It was accidentally discovered in 1964 by Arno Penzias and Robert Wilson, who initially thought the faint noise in their radio antenna might be pigeon droppings. The cosmic microwave background has been mapped with extraordinary precision by satellite missions and shows tiny variations in temperature of about 1 part in 100,000 across the sky. These variations are the imprint of quantum fluctuations from the inflation era, stretched to cosmic size, and they seeded the formation of all the large-scale structure in the universe. It is the oldest picture that can ever be taken. Galaxies are not randomly distributed through the universe. They are arranged in a vast cosmic web of filaments and clusters surrounding enormous empty voids, and the pattern extends across billions of light years. The large-scale structure of the universe looks, on the largest scales, like a three-dimensional web or sponge, with long filaments of galaxies connecting dense clusters at the intersections and vast empty regions called voids occupying the spaces between. The Milky Way sit within a local group of galaxies, which is part of a larger supercluster called Laniakea, which is itself part of the broader cosmic web. The largest known structures in the universe are immense sheets and walls of galaxies stretching for hundreds of millions to billions of light years. The Hercules Corona Borealis Great Wall is a structure of galaxies estimated at around 10 billion light-years across, so large that it challenges the assumption of cosmological homogeneity, the expectation that on large enough scales the universe should look the same in every direction. How this structure formed is difficult to reconcile with standard cosmological models, and it remains one of the most intriguing puzzles in observational cosmology. The cosmic web is a universe's architecture built from the gravitational amplification of tiny early fluctuations over billions of years, and it is a framework within which every galaxy, every star, and every planet has its address. Stars are born inside clouds of gas and dust, and the process of their formation is one of the most productive and violent in the universe. Nebulae, the vast clouds of hydrogen and helium from which stars form, are typically many light years across and extraordinarily sparse by any earthly standard. Gravity pulls the gas and dust together into denser regions, but heat resists collapse, and the process requires something to tip the balance toward contraction. A nearby supernova explosion, the passage through a spiral arm, or the collision of gas clouds can provide the trigger. Once a region begins collapsing, it fragments into multiple smaller clumps, each of which continues to contract independently, which is why stars almost always form in clusters rather than in isolation. As a collapsing clump shrinks, it heats up, and the growing ball of hot gas is called a protostar. When the core temperature reaches about 10 million Kelvin, hydrogen fusion ignites, and the protostar becomes a true star, with the outward pressure the energy produces balancing the inward pull of its own gravity. This balance, called hydrostatic equilibrium, can be maintained for millions to billions of years depending on the star's mass. More massive stars burn hotter and faster, and end their lives in spectacular explosions. Less massive stars burn slowly and quietly for tens of billions of years. The Sun is a middleweight star about halfway through its life, settled into a stable burning that has barely changed in billions of years. When a massive star dies, it does so in an explosion so bright it can briefly outshine an entire galaxy, and the elements it forges and scatters become the raw material for future generations of stars and planets. A supernova releases more energy in a few seconds than the Sun will emit in its entire 10 billion year lifetime. The explosion is triggered when the iron core of a massive star, which cannot release energy through fusion, collapses under its own gravity in less than a second, bouncing back as a shockwave that tears the outer layers of the star apart. The temperatures and pressures in the collapsing core and in the shockwave are so extreme that they forge elements heavier than iron, including gold, platinum, and uranium, which cannot be produced in normal stellar fusion. These elements are scattered into the surrounding space, enriching the gas cloud from which the next generation of stars and planets will form. Every atom of gold that has ever been mined, every atom of platinum, and every catalytic converter was forged in a stellar explosion or in the collision of neutron stars, which also produces these heavy elements in enormous quantities. The iron in your blood was made in the core of a star that lived and died before the Sun was born. Every heavy element in every living body is the product of stellar nucleosynthesis and stellar death. We are, in the most literal sense, made of star material. Neutron stars are the densest objects in the universe that have a surface, and their properties push the laws of physics into conditions that no laboratory on Earth can reproduce. When a massive star collapses, if the core that remains is between roughly 1.4 and 3 solar masses, the result is a neutron star rather than a black hole. A typical neutron star packs more than the mass of the Sun into a sphere about 20 kilometers across, giving it a density so extreme that a teaspoon of neutron star material would weigh roughly 4 billion tons. Gravity at the surface of a neutron star is approximately 200 billion times stronger than at the surface of the Earth. The interior of a neutron star is one of the most exotic environments in the known universe, where matter is compressed beyond atomic structure and protons and electrons are forced together to form neutrons. In the deepest layers, conditions may allow exotic forms of matter to exist that have never been created or studied in any laboratory, including quark matter and strange matter, whose properties are described by theories that have not yet been tested at those extremes. Neutron stars spin rapidly, and some spin hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. The magnetic fields of neutron stars can be trillions of times stronger than any magnetic field ever produced on Earth. They are objects that make extreme sound like an understatement. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. They form when sufficient mass is concentrated in a small enough volume, which happens when the most massive stars collapse at the end of their lives, and possibly through other mechanisms in the early universe. The event horizon is not a physical surface. It is a mathematical boundary defined by the geometry of space-time, beyond which all possible paths lead inward. Nothing that crosses it can communicate with the universe outside. What lies inside the event horizon is unknown. Our best theory of gravity, general relativity, predict a singularity at the center where density becomes infinite and the theory ceases to have meaning, but this is widely understood to signal the limits of the theory rather than a true description of physical reality. A quantum theory of gravity that has not yet been developed would be needed to describe the interior accurately. Black holes range enormously in size, from stellar mass black holes a few times the mass of the Sun to supermassive black holes at the centers of galaxies that can contain billions of solar masses. The first direct image of a black hole, the shadow of the supermassive black hole at the center of galaxy M87, was released in 2019 by the Event Horizon Telescope collaboration. It showed exactly the shadow predicted by general relativity, confirming a prediction made over a century ago by Einstein's equations in conditions more extreme than Einstein himself likely imagined would ever be observed. Gravitational waves are ripples in the fabric of space-time produced by accelerating masses, and their direct detection in 2015 opened an entirely new way of observing the universe. Einstein predicted gravitational waves in 1916 as a consequence of general relativity, but he doubted they would ever be detected because they were expected to be so faint. A century later, the LIGO detectors in the United States measured a distortion in space-time smaller than 1,000th the diameter of a proton, produced by two black holes a billion light-years away merging into one. The signal lasted about a fifth of a second and swept upward in frequency like a brief chirp, matching predictions for a binary black hole merger with remarkable precision. Since that first detection, gravitational waves have been measured from dozens of merging black hole pairs, from collisions between neutron stars, and possibly from mixed black hole and neutron star mergers. The neutron-star collision detected in 2017 was also observed simultaneously by conventional telescopes across the electromagnetic spectrum, inaugurating the era of multi-messenger astronomy in which the same cosmic event is studied through both gravitational waves and light. Gravitational wave astronomy allows us to observe the universe in a completely different medium than light, detecting events and objects that may be entirely invisible electromagnetically. Objects that produce no light at all, like colliding black holes, have become some of the most studied sources in modern astrophysics. The expansion of the universe is accelerating, driven by a mysterious force called dark energy, and the discovery of this acceleration is one of the most unexpected findings in the history of cosmology. In the 1990s, two independent teams of astronomers were studying distant Type Ia supernovae, which can be used as standard candles to measure distances across the universe because they always explode with approximately the same intrinsic brightness. The teams expected to find that the expansion of the universe was slowing down under the mutual gravity of all the matter within it. Instead, they found that distant supernovae were dimmer than expected, meaning they were farther away than the deceleration model predicted. The universe was not slowing down. It was speeding up. The expansion is accelerating, and something is driving it. That something was called dark energy, but the name conceals profound ignorance. We do not know what dark energy is. The simplest interpretation is that it is a property of empty space itself, a cosmological constant that Einstein originally introduced and then abandoned, which turns out to have been closer to right than he knew. Other interpretations include a dynamic field that evolves over time or modification to general relativity on cosmological scales. Distinguishing between these possibilities requires more precise measurements of the expansion history of the universe, and multiple observatories and missions are dedicated to this task. The fate of a universe depends on what dark energy turns out to be. The universe contains at least 2 trillion galaxies, each containing hundreds of billions of stars, and the numbers involved in describing it resist ordinary comprehension. The 2 trillion galaxy estimate comes from a study published in 2016 that combined data from deep field images taken by the Hubble Space Telescope with models of galaxy evolution and the universe's expansion history. Most of these galaxies are too faint and too distant to be detected with current instruments. They exist beyond the reach of our telescopes, but within the volume of the observable universe. A typical galaxy contains between 100 billion and 1 trillion stars. Multiplying those numbers together gives a total stellar count in the observable universe of somewhere in the range of 10 to the power of 24, a number with no meaningful everyday comparison. The total number of potentially habitable planets is unknown, but is estimated by some researchers to be in the billions within our galaxy alone, and in numbers that approach or exceed the total number of stars given the multiplier galaxies. The observable universe is not all there is. It is a sample of a whole that may be vastly larger, possibly infinite. To look at a patch of dark sky between the visible stars is to look at a region containing millions of galaxies, each with hundreds of billions of suns, many of which are planets, some of which are conditions suitable for chemistry as complex as life. The scale of the universe does not diminish what happens within it. It amplifies it. The Milky Way galaxy is a barred spiral galaxy about 100,000 light-years across, and the solar system sits in a relatively quiet region far from both the center and the outer edge. The galaxy contained between 200 and 400 billion stars arranged in a flattened disk with spiral arms winding outward from a central bar-shaped structure. At the center of the galaxy lies a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. Its presence is inferred from the orbital motion of stars near the galactic center that have been tracked over decades, their paths curving around an invisible mass with a precision that leaves no serious doubt about the black hole's existence and size. The solar system orbits the center of the galaxy at a distance of about 26,000 light-years, completing one orbit every 225 to 250 million years, a period sometimes called a galactic year or cosmic year. In the time since the Earth formed, it has completed roughly 18 to 20 galactic orbits. The Sun and its planets currently sit between two spiral arms in a relatively calm region with lower than average stellar density and radiation levels. Whether this relatively sheltered position has been significant for the development of life on Earth over geological timescales is a question that cannot easily be tested, but is considered by researchers who think about the conditions that favor the emergence of complex life. Quasars are the most luminous objects in the known universe, and they are powered by supermassive black holes consuming material at an extraordinary rate. A quasar, which stands for quasi-stellar object, is a brilliantly luminous core of a distant galaxy in which a supermassive black hole is actively accreting gas at a very high rate. As the gas falls toward the black hole, it forms a disk, and the friction and compression in this disk heats a material to extreme temperatures, causing it to radiate across the entire electromagnetic spectrum with a luminosity that can exceed that of the entire rest of the host galaxy by factors of hundreds or thousands. Quasars are so bright they can be seen across billions of light-years, which means they are also seen as they were billions of years ago, when the universe was much younger. Most quasars are found at high redshifts, corresponding to early cosmic times, and the relative scarcity of quasars in the local universe reflects the fact that most massive galaxies have now consumed the available gas in their central regions, and their black holes have become quiescent. The Milky Way's central black hole, Sagittarius A star, shows only faint and occasional activity today but may have been a quasar in the distant past. The jets produced by some quasars extend for millions of light-years in both directions, carrying enormous amounts of energy out into the intergalactic medium and influencing the formation of galaxies across vast distances. The fate of a universe is not known with certainty, and it depends on properties of dark energy and the total energy content of the cosmos that we have not yet measured with sufficient precision. Several scenarios are possible depending on how dark energy behaves over cosmic time. If dark energy remains constant, the universe will continue expanding forever, with galaxies beyond our local group gradually receding beyond our observational horizon. Stars will continue to form for perhaps another 100 trillion years, but as the supply of gas is consumed, star formation will slow and eventually stop. Existing stars will burn out one by one, and the universe will become progressively darker and colder in a scenario called a heat death, in which all available energy gradients are exhausted, and the universe reaches a state of maximum entropy with no further processes possible. If dark energy grows stronger over time, the expansion could accelerate without limit in a scenario called the Big Rip, in which the fabric of space-time eventually tears apart galaxies, then solar systems, then individual atoms in a sequence of disassembly working from the largest scales to the smallest. A third possibility, the Big Crunch, in which gravity eventually overcomes expansion and the universe collapses back on itself, is currently considered unlikely given the observed acceleration. Other scenarios involving quantum processes over extraordinarily long timescales include vacuum decay, in which the quantum state of empty space itself transitions to a lower energy state in a bubble that expands at the speed of light and rewrites the laws of physics everywhere it reaches. These are not science fiction. They are serious physical possibilities derived from current theory. The universe may be just one of many universes in a vast multiverse, and the idea arises naturally from several independent areas of physics rather than from speculation alone. The inflationary model of the early universe suggests that inflation may not have ended everywhere simultaneously. In regions where it ended, universes like ours formed. In regions where it continued, Space kept expanding, potentially spawning an infinite number of separate bubble universes, each with its own physical constants and initial conditions. This eternal inflation scenario produces a multiverse in which our observable universe is one bubble among an indefinitely large number. Separately, the many worlds interpretation of quantum mechanics proposes that every quantum measurement causes a universe to branch into multiple versions, each containing one of the possible outcomes, all equally real. The string theory landscape proposes an enormous number of possible vacuum states, each corresponding to a universe with different physical laws and constants, and suggests that all of these may be realized somewhere in the multiverse. The challenge with all multiverse proposals is that the other universes, by definition, do not interact with ours in ways that are currently detectable, which makes experimental testing extremely difficult. Critics argue that an untestable hypothesis is not scientifically meaningful. Supporters argue that if the theory makes correct predictions about our own universe, the multiverse may be an unavoidable implication. The debate sits at the frontier of what physics can currently address, in the territory where science and philosophy overlap. Time itself may have had a beginning, and the question of what, if anything, came before it is one of the deepest puzzles in all of human thought. General relativity describes a universe as a four-dimensional space-time, where time is a dimension of the fabric of the cosmos rather than a fixed and universal backdrop. If that fabric had a beginning in the Big Bang, then time itself began, and the question of what came before has no more meaning than the question of what is south of the South Pole. The universe would not have appeared in time. Time would have appeared with the universe. This view, associated with the physicist Stephen Hawking and his collaborators, implies that the question of a cause for the universe may be grammatically meaningful but physically empty, since causation requires time and time did not exist before the universe. Other proposals suggest that time is not fundamental but emerges from a deeper, timeless quantum state, the way temperature emerges from a collective behavior of many particles that individually have no temperature. In this view, time as we experience it is an approximation that breaks down at the quantum cosmological level. Still other proposals allow for a quantum state without classical time from which the universe could emerge probabilistically without a specific cause. The nature of time, whether it is fundamental or emergent, whether it had a beginning, and whether the concept of before applies to the universe as a whole, remains one of the most open and extraordinary questions in science. The universe is almost incomprehensibly old, but has a surprisingly recent stellar population, and many of the stars visible tonight formed long after the universe was already middle-aged. The first stars formed a few 100 million years after the Big Bang in a universe that contained only hydrogen, helium, and a trace of lithium. These first stars, called population 3 stars, may have been much more massive than stars today, burning hot and fast and ending in supernovae that seeded the universe with its first heavy elements. No population 3 star has ever been directly observed, because they are expected to be so distant and because they live so briefly in cosmic terms that finding one requires looking extraordinarily far back in time. The next generation of stars, called population 2 stars, formed from gas enriched by those first supernovae and are found today in the oldest parts of galaxies, including the dense star clusters called globular clusters that orbit the Milky Way. Our Sun is a third-generation population 1 star, formed from gas enriched by multiple generations of previous stellar evolution, which is why it contains a relatively high abundance of heavy elements, including the carbon, oxygen, iron, and calcium that make up the planets and the life around it. The universe had to go through several generations of stellar birth and death before it could produce the heavy elements needed to build rocky planets and biochemistry. Life required a universe to age first. Exoplanets orbit stars beyond our Sun in extraordinary variety, and the survey of them has overturned almost every assumption astronomers held about how planetary systems form and what they look like. Before the first confirmed exoplanet discovery in the 1990s, the solar system was the only planetary system known, and it was assumed to be relatively typical. Subsequent discoveries have revealed a universe of planetary diversity that the solar system does not adequately represent. Hot Jupiters, gas giant planets orbiting closer to their stars than Mercury orbits the Sun, are common and have no equivalent in our solar system. Super-Earths, planets larger than Earth but smaller than Neptune, are one of the most abundant types of planet found and are completely absent from our solar system. Many planetary systems have multiple planets packed in close orbits, all completing their years in what would be the innermost region of our solar system. Some planets orbit in the habitable zones of their stars, at distances where liquid water could exist on the surface, and several such planets have been found orbiting nearby stars. The variety of stellar environments, from hot blue giants to cool red dwarfs, each with their own planetary systems, has expanded the context in which the question of life elsewhere in the universe is asked. We now know that planets are ubiquitous, that almost every star likely has at least one, and that rocky planets and habitable zones are common enough to exist in very large numbers across the galaxy. Some stars end their lives not as supernovae, but by slowly shedding their outer layers into space, creating some of the most beautiful structures in the observable universe. When a star like the Sun exhausts the hydrogen in its core, it expands into a red giant, eventually shedding its outer layers in pulses and stellar winds that form an expanding shell of glowing gas around the dying stellar core. These structures, called planetary nebulae despite having nothing to do with planets, are illuminated by the ultraviolet radiation of the hot stellar remnant at their centers, which excites a gas and causes it to emit light in specific colors determined by its composition. Oxygen emits green and blue-green light. Hydrogen glows red. Nitrogen adds its own spectral signature. The result can be strikingly symmetrical structures, rings, bubbles, and hourglass shapes that span light years and glow with an ethereal beauty visible across thousands of light years. The Ring Nebula, the Helix Nebula, and the Cat's Eye Nebula are among the most photographed objects in the sky for precisely this reason. The symmetrical shapes are produced by the interaction of multiple episodes of mass loss, magnetic fields, and in many cases a gravitational influence of companion stars shaping the outflow. What remains at the center after the nebula disperses is the stellar core itself, a white dwarf, which will cool slowly over billions of years without ever undergoing fusion again, fading from white to yellow to red to black in a timescale longer than the current age of the universe. The question of whether we are alone in the universe is one of the oldest questions humanity has asked, and the scientific search for an answer is only a few decades old. The universe contains trillions of planets, many of them rocky and orbiting at distances from their stars where liquid water might exist. The chemistry of life, based on carbon and involving amino acids, sugars, and nucleotides, uses elements that are among the most abundant in the universe and that form spontaneously under a wide range of conditions. Amino acids have been found in meteorites. Complex organic molecules have been detected in interstellar gas clouds. The ingredients of biochemistry are apparently common. Whether they have assembled into life elsewhere remains unknown, but the question has moved from philosophy into scientific investigation through the search for biosignatures in exoplanet atmospheres, the continued listening for radio and optical signals from technological civilizations, and the study of extreme life on Earth to understand conditions under which biology can persist. The Fermi paradox, which asks why we have not yet detected any sign of other civilizations given how many opportunities for life appear to exist, remains unresolved. Possible resolutions range from life being genuinely rare in its origins, to civilizations being short-lived, to the possibility that other civilizations exist but that interstellar communication is far more difficult than it appears from here. Each answer carries its own implication for what we are and where we stand in the universe. The universe contains structures on scales so large that light from one side of them could not reach the other side in the entire history of the cosmos. The Hercules Corona Borealis Great Wall is estimated to span approximately 10 billion light years. The universe is only 13.8 billion years old. A photon of light traveling since the Big Bang would have crossed only a fraction of this structure in all that time. This creates a conceptual difficulty for standard cosmology, which assumes that on large enough scales a universe should be smooth and uniform because regions that were once in contact have had time to equalize their properties. A structure so vast that its different parts could never have been in contact with each other seems to challenge this assumption. Some researchers suggest the structure may be a statistical artifact of the way the galaxy survey data was analyzed. Others take it as evidence that our cosmological models are missing something. Similar debates surround other large structures, including the Sloan Great Wall and the Giant Arc. The universe keeps producing structures at ever larger scales as surveys cover larger volumes, and each new discovery restarts the conversation about whether there's truly a scale at which the universe becomes uniform or whether the cosmic web extends in complexity all the way to the horizon and beyond. The largest things in existence are still being found. Empty space is not empty. It seethes with quantum activity, and the energy of this vacuum may be connected to the dark energy that is accelerating the expansion of the universe. Quantum field theory, one of the most precisely tested theories in physics, predict that empty space is filled with fluctuating quantum fields that constantly produce and annihilate pairs of virtual particles. These fluctuations carry energy, called zero-point energy or vacuum energy, and they have measurable physical effects. The Casimir effect, in which two uncharged metal plates placed very close together in a vacuum experience an attractive force, is a direct measurement of vacuum energy and confirms that the quantum vacuum has real physical consequences. The problem is that when physicists calculate the expected energy density of the quantum vacuum and compare it to the observed energy density of dark energy, the numbers disagree by a factor of around 10 to the power of 120, the largest discrepancy between a theoretical prediction and an observed quantity in the history of physics. Something is almost certainly missing from the calculation, a cancellation mechanism or a symmetry that dramatically reduces the vacuum energy. Finding what that missing piece is would be one of the most significant theoretical advances possible, potentially illuminating not just the nature of dark energy but the foundations of quantum field theory and cosmology together. The silence of empty space is one of the loudest unsolved problems in physics. The universe had almost equal amounts of matter and antimatter in its first moments, and the reason there's anything left over is one of the deepest unsolved problems in physics. Every particle of ordinary matter has a corresponding antiparticle with opposite charge but otherwise identical properties. When a particle meets its antiparticle, they annihilate each other, converting entirely to energy. In the very early universe, matter and antimatter should have been produced in equal amounts and should have annihilated each other completely, leaving a universe of pure energy with no matter at all. Yet here we are, made of matter, living on a planet of matter, in a universe that appears to contain vastly more matter than antimatter. For every billion antiparticles produced in the early universe, there appear to have been 1,000,000,001 particles of ordinary matter. The tiny asymmetry survived the great annihilation and became everything that exists. The physical process that produced this asymmetry is called baryogenesis, and while the conditions required for it are known in principle, the specific mechanism that operated in the early universe has not been identified. Experiments search for subtle differences in the behavior of matter and antimatter that could account for the asymmetry, and small violations of the expected symmetry have been found, but not large enough to explain the degree of matter dominance we observe. The existence of the universe, of every galaxy and star and atom and living thing within it, is a consequence of a tiny imbalance in the first second of time whose cause we do not yet understand. The possibility that the universe is a simulation has moved from science fiction into a subject of serious philosophical and scientific discussion. The argument, in its most rigorous form, was formalized by philosopher Nick Bostrom in 2003 and proceeds from the observation that if civilizations can create detailed simulations of conscious minds, and if they choose to run many such simulations, then the number of simulated minds would vastly outnumber real ones, making it statistically likely that any given mind is simulated. Some physicists have noted that the universe has mathematical properties that seem suggestive of computational structure, including the discrete nature of space-time at the Planck scale, the finite speed of information processing implied by the speed of light, and the apparent fine-tuning of physical constants that is easier to understand in the context of a designed system than a random one. Others have pointed out that any evidence we could find within the simulation would by definition be part of the simulation and could not distinguish it from a base reality. The simulation hypothesis is therefore currently untestable in any direct sense, though some researchers have proposed that certain signatures of computational limitations might in principle be detectable in the physics of cosmic rays or in the large-scale structure of space. Whether or not the idea is taken seriously as a physical hypothesis, it functions as a profound philosophical question, asking what it means for something to be real and whether the distinction between a perfectly detailed simulation and reality has any meaning at all. And through it all, the deepest mysteries stay closest. The universe is 13.8 billion years old and still going, still expanding, still building and destroying and recycling its contents on timescales that make human history feel like the briefest of introductions. We drifted past the first 3 minutes of time when hydrogen and helium condensed from a hot plasma. We listened to space itself ring like a bell when black holes 1 billion light years away merged into one. We watched light from the edge of the observable universe carry a message sent 380,000 years after the beginning, still arriving, still telling us what the infant universe looked like before it knew what it would become. We visited the quiet violence of stellar nurseries and the peaceful disintegration of dying stars into glowing shells of colored gas. We found that most of the universe is made of things we cannot see and is driven by a force we cannot explain. We asked whether time had a beginning and whether the universe is one of many, and found that these questions sit at the very limit of what any instrument or theory has yet been able to reach. And through it all, The universe simply continued, vast and patient and indifferent to our curiosity, but never, not once, running out of things to offer it. The universe does not need to be understood to be extraordinary. It simply is, on a scale and for a duration that quietly exceeds everything we know how to feel. If you enjoyed this sleepy journey, you could support the channel by liking, subscribing, or leaving a calm little comment before you rest. It helps more curious minds find their way here. And if you are still awake, there's another video waiting on your screen, ready to carry you onward into another corner of science. But for now, let the questions loosen their grip. Let your shoulders soften. Let your jaw unclench. Allow your breathing to slow, steady, and deepen. Picture the night sky above you, dark and vast and full of light that left its source before you were born. Every star, son. Every gap between them a distance too large to walk. And hey, in the middle of all of it, you, breathing quietly, held by a planet, warmed by a star, made of atoms forged in fires that ended long before the earth existed. You do not need to understand it all tonight. You only need rest. Sleep well, and good night.